Hello, welcome to another Teacher Tobin video. We're going to be exploring the topic of binary shifts under the Edexcel GCSE Computer Science program. This will cover the specification 2.1.4, and there are two types of shifts you need to know about: logical and arithmetic shifts. Students usually mess up arithmetic shifts because they forget that some of the rules associated with it. Generally speaking, arithmetic shifts, especially when we're dealing with arithmetic shifts right, are dealing with signed integers. So the only two signs an integer can have are positive and negative. So if we're dealing with a negative number, like I say, a 2's complement number, we'd generally be using arithmetic shifts. Logical shifts on unsigned integers, positive binary numbers. Logical shifts are easier, so let's look at that first. So I'll just give you a quick example to get going. I'm going to add some columns here for my binary values. Just put a 5-bit system in here, just to keep these things simple. Go back to my very first video on binary if you can't remember where these numbers are derived from. But they're all turned into base 2, 2 to the power of 0 is 1, 2 to the power of 1 to 2, etc. So let's say I've got a 9. Okay, so how do I represent a 9? Well, 16 doesn't go into that, 8 does go into 9, and then I need the 1 to make 9, so that's a 9. And I want to see what happens if I shift this binary number either left or right. What happens to it? Well, let's try shifting it over to the left, and that's going to be the equivalent of timesing this number by 2, and let's see if we can prove it. So I'll just put a little dash down here so it's easier to see what's going on with the different columns. Okay, so if we shift everything over, and there are some rules that we've got to remember when we're doing this, but let's try and make it as clear as possible. So I'm shifting everything to the left, so that 0 goes over here. I mean, in fact, we don't even have to worry about it, it's just 0. That 1 goes here, so that's 1. I'm going to put that in there just in case. That 0 is going to go over here, 0. That's going to go here. And that 1 is going to go over here, and then I'm going to fill up the gap with a 0. So that's the first big rule there. I'm going to fill it up with a 0. So what do we expect it to be? 9 times 2 is 18. We expect it to be 18. Is it 18? Well, we've got a 16 and then we've got a 2. So 16 plus 2 does equal our 18. Happy, we're good with that. So moving it to the left successfully multiplied it by 2. What happens if we go the other way? Let's do a right shift, a logical right shift. We're going to do the same as dividing it by 2 then. Now you might have spotted the potential error that creeping in here, or it could be a possible problem. So let's just extend these little columns down, just so it's easier to see what's going on. Okay, so our original number was here. Now this 0 is going to go into this column. That 1 is going to go over here. That 0 is going to go over here. That 0 is going to go over here. Now we've got an issue. This 1 has got nowhere for it to go. So it's just going to be removed. And we've got a space over here which we can just fill with the 0. So what is this column worth? Well, it's just worth 4. And we would expect 9 divided by 2 to equal 4.5, wouldn't we? But because we've lost a bit of information, we've only got the 4 left. So yes, it's a flawed way of dividing. I mean, especially for negative numbers, you are in danger of removing information on either side, depending on if you're doing too many left shifts and you don't have enough bits to store it in. But you don't need to worry about how computers handle that in real life, other than the fact that how it works. So we put any gaps in with zeros with logical left and right shift, and we saw that 9 shifting it over one position to the left, times it by 2, and shifting over at one position to the right, divided by 2. We could shift left again, and it would times by 2 again. So we would get our 36. We could do that quickly, couldn't we? So let's just see what would happen. That would go over here. Then we'd have the 0, 0, 1, 0. So that would be a 0. So 36, 32 plus our 4 is our 36, isn't it? So if we shifted it over again, if we left shifted it over again, we would get our 36. Let's do it on a bigger number. I'm just going to make one up just off the top of my head. Don't know what it is. And let's say we've been asked to logical shift left and timesing by 4. Okay, so we want to times this number by 4. Well, how would we do it? I'm just going to make some little columns here to make it easier to see what's going on. The first shift over, everything's going to be moved over to the left. So let's do that. So that 1 is going to go over here. That 0 is going to go in this position. That 1 is going to go over here. That 1 is going to go there. Then the 0. Then the 1 is going to go there. Then that 1 is going to go here. Then that 0 is going to go here. And we're going to fill in the gap with a 0. So that's just going over one time. So that would have times this number by 2. And then if we go again, that 1 is going to go into this column. 0 is going to go here. 1 is going to go here. 1, 0, 1, 1, 0, 0, 0. So the issue here is we've got to have a 10-bit system to store this logical shift left, because we're timesing this number, which we know has got 128 in it, by 4. Okay, so it's going to be a pretty big number. I mean, that column is worth 512, and we've got a 512 in there, plus 128. So we would potentially come up with some issues of overflow if we didn't have enough bits to store that resulting left shift. We don't want to be in a position where we're losing that most significant bit, because it'd be quite significant. I mean, the difference between that number and what it should be can result in real world issues. I mean, there have been problems with rockets crashing because of conversion issues between 16-bit numbers. So real world consequences to things like this. But that was just an example, just to show you how we can shift it over. The main thing to take away there is that we added the 2 zeros there to fill in the gaps. And if we moved it right, we would do the same thing. We would just fill in the zeros this way if we wanted to divide by 4. Now, what is the difference between a logical shift where we just fill in with zeros on either side and an arithmetic shift? The arithmetic shift is where we preserve the most significant bit. So I'm going to use the exact same binary number that I did before, which I just made up out of thin air. But let's do an arithmetic shift left to this, and then an arithmetic shift right to this. Now, easy to remember, an arithmetic shift left is the same as a logical shift left. It's just the same. So if we move this over, we can just fill it with zeros, no problem. We're okay with that. But where it gets tricky is where we arithmetic shift to the right. So I'll do the left one first, just so to prove it to you. So if I wanted to do a left shift timesing by 2, I could move that 1 over there. That 0 then goes into this place. 1, 1, 0. So you can see that they're all shifting over. 1, 1, 0. And I can just fill the gap with that 0 there. All right. So it's the same as timesing by 2. No problem. So arithmetic shift left, we don't have an issue. Problem's going to be if we go right. Now, as I said to you before, arithmetic shifts are generally on signed integers. So let's just assume right now that if we're doing an arithmetic right shift, we're dealing with a signed integer, which means that this column here is minus 128. So let me I'm going to just erase a little bit of here. Is that going to let me erase it? No, okay, fine. So that's going to be 128, that's going to be 64, 32, 16, 8, 4, 2, and 1. And if you can remember from the last video, we've got a range from minus 128 to positive 127. That's what we can represent here. So what this would be, this first number, if we were dealing with a signed integer, we know it's a minus number because we've got a 1 here. Okay, we know it's a minus number. And if we add 32 to it, so it's essentially it's 128 plus 32, and then plus 16, plus 4, plus 2. All right. So what we could do it? So 32 plus 16 is 48. So that's minus 80. It's minus 80, and then plus 4, minus 76, and then plus 2, minus 74. So I'm pretty sure that's minus 74 as a number. So what we could do is then divide this using a logical right shift. Let's say we want to divide by 2, so we're just going to shift 1 place to the right. So just for the moment, ignore this one. That was the left shift one, ignore that. Let's have a look at it. So that 1 and this is the key difference between logical shifts and arithmetic shifts. That 1 needs to stay exactly where it is, because if we moved it, our number would no longer be minus anymore. And we know that minus 74 divided by 2 is going to be minus 37, right? We know that. We've got to make sure that whatever we end up with is minus 37. So we preserve that 1. We preserve the MSB, the most significant bit. And we've got a gap then. Okay, we've got a gap. So that 0 is just going to go away. We've lost that 0. That 1 is going to go into this place. That 1 is going to go over here. That is going to go over into the 3rd column. That is going to go over here. That's going to go over here. We've got this 0 over here, and then that 1, what we need to do is fill it with whatever the value of our most significant bit was. So we fill that up with a 1. We fill that with a 1. So let's work this out. If we've done it correctly, this whole number here Let me just write it out again, neater. Should equal minus 74 divided by 2, which is minus 37. Right, it should equal that if we worked it out. So I'm going to just make sure that's noted as minus 128. That's plus 64. That's plus 16. That's plus 8. That's just 2, and that's plus 1. So if we have a minus 128 plus 64, we have minus 64, right? Then minus 64 plus 16 is 58, 48, minus 48. And then plus 8 is, so it's minus 40. And then minus 2 is minus 38, and then finally the minus 1 is minus 37. So we've just proved that shifting everything to the right is minus 37 as we wanted it to be, as long as we don't mess up the most significant bit and we fill in any gaps with the value of the most significant bit. Let's do another example, because I know that this is a bit of a tricky concept. In fact, let's just look at some exam questions first. Shifts are performed on binary patterns. A logical shift right is performed on a pattern. Fine. An arithmetic shift right is performed on the same original pattern. Describe the reason the results will be different. Okay, so it's a 2-mark. So you're going to have a linked explanation, or at least write 2 relevant things, because it doesn't say, the command word doesn't say explain here. So, but you need to have at least 2 things for the examiner to mark. So it's essentially what we just talked about. You would need to start using terminology like MSB. So you can say a logical shift fills gaps left or right with zeros. And if you could, you could even, just to make sure that the examiner knows that you understand, with a left shift being equivalent of times them by 2. I'm just abbreviating here. And right divided by 2. Now that should easily give you at least one of the marks, but you've got to have 2 marks, because they really want you to demonstrate that you understand what arithmetic shifts right are. So you can say, whereas arithmetic shift, the MSB, the most significant bit, is preserved. Sorry, my writing on the tablet's not great. Is preserved, and any gaps are filled with the value of the MSB. It should be noted, if you had a positive number and did an arithmetic right shift, you would just have zeros and it'd be fine. You can fill with zeros. But 9.5 times out of 10 arithmetic right shifts are going to give you that 1 on the left hand side, because it's really to do with signed integers. So let's just do one more. Oh, hang on, we've got one more question here. Computers carry out mathematical operations, give the result of applying a logical shift left by 2 to the... Okay, so we've got this number here. let's just shift it. Let's shift it left. So we're timesing by 2. We move it over one side. So that goes here, that goes here, that goes there. 1, 0, 1. Just making sure that I'm not messing this up because it's really tricky sometimes to visualize it. That, I'm going to use a different color. That 0 goes over here. That 0 is going over here. That one's going there. That one's going there. That 0 is there. That one's there. We're going to have another 1 here. That's fine. That 0 is here, and then we replace the gap with, because it's a logical shift, we just replace that with a 0. So what is this number? It's 32, 16, 4 and a 2. So 16 plus 4 is 20, plus 32 is 52, plus, so it's 54. So I expect this number to be 108. So let's just make sure it is. 64 plus 32 is 96, plus 8 is 104. Plus our 4, which is here, is 108. So if I couldn't quite remember the rules for logical shift, I know what 54 times 2 is. So I've just got to make sure that my resulting binary number equals 108. And you can just use the totals. If you want to, just write these in the exam just to make it easier. That's what I would do. And that would be worth 256, but of course it's a 0. And you'll get a mark for each nibble. If it's a 1 marker, okay, you just have to have the whole thing right, but sometimes they award 2 marks for each nibble. Good. So let's do one more arithmetic right shift. And again, I'm going to just make up a number. I'm going to make up a number. So let's spread them out a little bit this time. That's my first nibble. All right. So I've got my number here, and I'm just going to isolate the most significant bit here, so you can see where it is. So let's make this more tricky. Let's say we're dividing this by 4. So we're right shift twice. So we're going to shift it over to the right by twice. Let's see what happens. We know whatever we do, we've got to keep this here. So I'll do the first shift over, and then we'll do another one underneath. Okay, so we'll do the divide by 2, and then we'll do the divide by 4. How about that? So I'll write that underneath. So divide by 2, divide by 2. Make it a bit clearer. So here, we're going to have a bit of data loss here, aren't we? So that 0 is going over here, 1's over here, 0's over here, 0's over here, 1's there, 0's there. Now the 1, that 1, it's got nowhere for it to go. There's nowhere for it to go, so we're getting rid of that 1. It's gone. And we've got to make sure that we fill in the gap with whatever the value of the MSB was. And let's do the other one. So we've already got this. We know that's there. Let's move this over here. Move this one over here. This one over here. This one over here. This one over here. And the 0, we've lost that 0, but it didn't really matter because the 0 didn't contain any information. And then we've got to make sure that we fill in that gap with the value of the MSB again. So let's just actually figure out what that value was in the first place. it was, let me just use a different colour, minus 128, that's 64, that's 32, that's 16, that's 8, that's 4, that's 2. And I'm going to make the executive judgment this would have been acted on a signed integer, a minus number, because arithmetic right shifts generally are. So we start off with minus 128, and then we add 32 to it. And then we've got 4 and a 1, so in total it's 37. So let's just do this methodically. So minus 128 plus 32 is going to be minus 96. So I'm just going to put a little minus 96, and then adding 4 to it is minus 92, and then adding a 1 to it is minus 91. So we've got minus 91. Just making sure that I've done that right. 10 and 0, 1, 2. Yeah, that's right. So that equals minus 91. Now, if we divided that by 2, what would we expect that to be? We would expect it to be 45.1. But, sorry, 45.5. But we've lost this information here. So let's just total this up. So minus 128 plus 64 is minus 64. Plus 16 is minus 48. And then plus 2 is minus 46. I think I've done that right. Minus 58, 48. So 110100. So yeah, 46, and then because we can't get the full information there, the arithmetic right shift isn't perfect. Again, you're sort of losing information, and then we would expect that to be what, potentially 23 if we divide it again, minus 23 I should say, minus 46. So we've got minus 128 plus 64 is minus 64, plus 32 is minus 32, plus 8 is minus 24, and then plus the 1 is minus 23, which gives us our minus 23. So to performing 2 arithmetic right shifts onto our original minus 91 gives us that minus 23. Okay, if that was helpful for you, please let me know in the comments. If you would like me to explore any more of that, please also let me know. If any of it was helpful for you, also let me know.